Hello, my name is George Lockett and I'm going to talk to you about the North Sea Geothermal Power Project, which talks about the geothermal energy potential in the North Sea oil and gas industries. The Earth's crust, which contains the oil and gas hydrocarbons, makes up just 4% of the total mass of the planet. The remaining 99.6% is hotter than 500 degrees centigrade, going to 5,000 degrees C in the center. If you can imagine the continents like icebergs, then under the mountain ranges, the Earth's crust is about 70 kilometers thick, and on the coastal plains, about 40 kilometers thick. But as one moves offshore and we move into deeper water, we can see that the Earth's crust gets thinner both from the top and underneath as the mantle and the water level come closer together. This is why I'm putting forward the idea of tapping North Sea geothermal power. As one moves offshore, the geothermal gradient increases to 35 degrees per kilometre depth. If you look at the map of the fields and pipelines within the UK North Sea, there's approximately 230 oil fields and 100 gas fields. There's been over 2,900 oil wells drilled and 1,200 gas wells drilled. There are currently about 450 structures in the North Sea, with a decommissioning cost of between 30 and 45 billion pounds. But a lot of these structures have only been in place for about 30 to 40 years. And a lot of the structures have a useful life of, especially the concrete structures, of over 300 years. Therefore, what I'm suggesting is that geothermal could be an alternate use for these North Sea structures. So instead of extracting the oil and gas and bringing it ashore and burning it to generate the heat, that we just use the natural heat offshore to generate the power directly without any of the emissions that you get from burning fossil fuels. One of the advantages of using North Sea structures is that the platforms from which they're drilled from quite often drill multiple wells from the same rig. If you know about geothermal power, the most common system is enhanced geothermal recovery. What that means is that you pump water down one or two wells and then receive the steam or hot water at alternate wells after it's passed through the fractured rock structure, which transfers the heat to the water, which is the working fluid. It then comes up to the surface and quite often goes through a heat exchanger so that only a clean working fluid passes through the turbines and generates the power, and then the water is re-injected, so there's no pollution. It's a completely enclosed system, and all you're transferring is the heat from the geothermal field up to the turbines where the power is produced. Jobs and carbon credits. Geothermal could create a whole new North Sea industry, employing thousands of workers in new productive jobs in the offshore and onshore support industries. Geothermal power holds enormous opportunities to provide affordable clean energy that avoids greenhouse gases like carbon dioxide. Geothermal energy is true baseload, producing electricity 24 hours a day, 7 days a week. The continental shelf in the UK, where these platforms are situated, has a relatively thin Earth's crust, about 10 kilometres thick, compared to 40 to 70 kilometres thick on land. giving the wells high bottom hole temperatures. Typical geothermal gradients of 35 degrees centigrade per kilometre have been recorded on the continental shelf. The Scottish Parliament has stated no nuclear power stations within the Scottish borders. Therefore, what I'm suggesting is that geothermal power may be an alternative to this lost power production of the nuclear power station. And again, as a nuclear power station operates 24 hours a day, 7 days a week, so also can geothermal operate 24 hours, 7 days a week, producing true baseload power. An example of the geothermal potential is the Earthskin high temperature, high pressure field. This includes bottom hole pressures of about 14,000 pounds per square inch and temperatures of 175 degrees centigrade. The wellhead shut-in pressure was 10,600 pounds per square inch at 150 degrees centigrade, with a water depth of just 300 feet. And this is located about 150 miles east of Aberdeen. The Elgin-Franklin field also has high temperature and high pressure. The largest high temperature, high pressure development is the Elgin-Franklin field. It's the world's largest, giving a pressure of 15,000 pounds per square inch and a temperature of 190 degrees centigrade. A new record-breaking well was drilled to a depth of 6,100 meters with a temperature of 197 degrees centigrade and a pressure of 16,750 pounds per square inch. This gives a geothermal gradient of 32 degrees centigrade per kilometre depth. So we can see from these examples that the geothermal energy is there already. Further geological studies and mapping needs to be done. What would be useful if all the oil companies could map the bottom hole temperatures of the wells as they drill them and produce three-dimensional maps which could have all the temperature bands logged together, and by doing this we could see where potential geothermal fields are located within the North Sea. So this is something that the oil companies can work on now, is to coordinate and collate the bottom hole temperatures of all their wells. And also, if you drill wells and strike water or steam instead of oil and gas, note the pressures of these water wells, these hydrothermal fields, and note the pressure of the steam, because it may be that as geothermal becomes more popular, that instead of just plugging and abandoning these wells, that they can still be used. We'll look now at the technology. Baker Hughes has got a demonstration site in America for enhanced geothermal system. They've drilled to a depth of 10,000 meters and produced temperatures of 300 degrees centigrade. And they've produced all metal bearing drill heads, which have special greases that can operate at these high temperatures. They've created a geothermal ultrasonic fracturing imager, which again can do the well logging at temperatures and show the fracture image of the fracturing of the reservoir. So the technology is already available to operate at 300 degrees centigrade. The design study that we're working on with the North Sea Geothermal Power Project may lead to the construction of 2 North Sea interconnector hubs to service the geothermal power offshore. One hub would be situated 100 miles east of Aberdeen, connecting Scotland and the Nordic countries, that's Norway, Sweden and Denmark. The second interconnector hub would be 100 miles east of Hull, interconnecting England, Holland and Germany. Deep geothermal is coming of age, and North Sea geothermal has huge potential when compared with nuclear. Here is some data of the nuclear fission reactor, which is now decommissioned at Cowler Hall Magnox plant. And one of the last of the Magnox reactors, the Wilbur Reactor 2 on Anglesey, stopped operating on the 25th of April. Therefore, there is a lack of energy coming from these nuclear power stations, which North Sea geothermal could step into to fulfill this need for an alternate source to nuclear. So if we look at detail at these nuclear flow rates, pressures and temperatures, we can see the flow rate was 180 tons per hour for the Calder Hall Magnox reactor. The pressure was 14 bar, about 200 pounds per square inch, and the temperature that it operated at on the steam cycle was 310 degrees Celsius. The current knowledge of the geothermal gradient in the North Sea at these 2 hotspots where the interconnectors will be situated is 35 degrees centigrade per kilometre depth. To have a temperature of 310 degrees C coming to the surface, we would need a bottom hole temperature of about 350 degrees centigrade or 10,000 metre depth. Lamprell has been recently awarded the contract for a jack-up rig to build a Super 116E enhanced class. This is designed to drill to 30,000 feet or 10,000 meters. It's going to be fabricated by Lamprell, and the project is planned to be completed in 2014. The purpose of this slide really is just to show that drilling rigs are capable today of drilling down to depths of 10,000 meters, and we've already seen that the Baker Hughes produce the drill bits, the muds and the logging equipment for operating at these high pressures and high temperatures. Deep geothermal is coming of age. The main difference in the above data will be the operating pressure. The Magnox had an operating pressure of 14 bar, about 200 psi. Geothermal well pressures may be much higher and may need to be controlled by a choke. For example, the Elgin Franklin is the world's largest high temperature, high pressure development. A new record-breaking well was drilled to a depth of 6,100 meters with a temperature of 197 degrees centigrade and a pressure of 16,750 pounds per square inch. So we can see that the natural geothermal pressure at these depths is much higher than in the Magnox reactor. As it is the pressure that does the work to generate the electricity, and as the pressures are so high, perhaps a lesser depth may be appropriate and still produce the same power as a Magnox reactor did, which was about 40 megawatts electrical per reactor, producing power 24 hours, 7 days a week. Geothermal reservoir and scope for licensing. So how big will the geothermal reservoir need to be to achieve the same flow rate as a Magnox reactor did, the 180 tons per hour? The answer to this and the size of the geothermal license may come soon from this Scottish Renewable route map team. Here's a quotation from a letter which I received from them last June. Further research still needs to be done. I explained in my previous letter that we would be commissioning a research program to identify the next step to take forward the commercial exploitation of deep geothermal energy, including the scope for licensing. This research is now underway and the results are expected to be available in spring 2013. So will the geothermal license be by depth? Remember the 35 degrees C per kilometre depth geothermal gradient, or by block, as in the oil and gas exploration industry? I think we will have the answer to this in the spring and summer of next year, and maybe the oil and gas exploration companies will add geothermal to their bow. For instance, I'm aware that BP and Chevron are also involved in geothermal exploration out in Indonesia. So it may be very easy for them to transfer the technology to North Sea geothermal energy. So where will we put these larger structures in the North Sea? What I would like you consider now is the Millbury Harbour, which was built in the Second World War. The Royal Marines built a complete Millbury Harbour out of 600,000 tons of concrete between 33 jetties and had 10 miles, 15 kilometres of floating roadway. What we could do is use the platform to anchor floating harbour walls, thus creating bigger offshore structures like geothermal power stations and interconnector hubs, and also harbours and helipads. So using this floating technology, which was used in the Second World War but brought up to modern day standards, we can build very large floating structures and use the decommissioned platforms as the anchor points to hold these in place, thus creating offshore power stations, interconnector hubs, small towns, harbours, heliports, helipads. There's a lot of possibilities available as we generate the power to power up these structures using the geothermal energy that we're tapping. There are three main types of geothermal energy. One is geopressure, is where you have high wellhead pressure, which you can put a hydroelectric type turbine on to generate the power. Two, separate the gas from the oil-water brine and use it in the diesel type generator. This can be used where there isn't enough gas for commercial production. Three is to use the temperature, as in the high pressure steam, the steam, organic Rankine cycle or deluge turbine system. These different systems we'll be discussing later, and I'll show you the different temperature bands which each operate in to produce the power. Secondary oil recovery and enhanced oil recovery. Geothermal heat can be brought from a lower level to steam flood oil deposit and create secondary oil in a mature field directly. Approximately 5,000 billion barrels are available worldwide. So the basic concept is this heat could be brought up to the platform first, generate electrical power, and instead of condensing the condensate, the heat could be returned to the oil field level to steam flood the reservoir for secondary oil recovery. Furthermore, it is also possible to discover lower oil and gas fields when drilling to greater depths to tap the geothermal energy under the platform. So just to give a little more overview about the secondary oil recovery, I mean, in Louisiana, for instance, what they're doing now is drilling an extra 5,000 meters, and they've found different layers of reservoir sand below the existing oil and gas wells that are becoming depleted. And the same thing may happen in the North Sea as we drill deeper to tap the geothermal energy. We may also discover these lower reservoir sands that have yet to be discovered reserves of oil and gas. And as this slide mentions, there's a huge quantity of heavy tars and heavy oils that can't be recovered unless the fields are steam flooded. So geothermal is a way where we can generate the power for this extra pumping and also generate the field pressures to do this secondary oil recovery. Cooling towers. Onshore geothermal normally uses air cooling tower with a wet bulb temperatures of 27 degrees centigrade. Offshore geothermal can take advantage of the large quantity of cold seawater at 5 degrees centigrade. Thus can often mean a 12-degree increase in temperature difference across the turbine. For instance, if we're using the deluge system, which operates at a temperature of 80 degrees centigrade and needs 100 degrees Fahrenheit temperature difference between the input temperature and the external temperature, using cold seawater means that we can have a lower input temperature, which means that virtually every geothermal, every location in the North Sea can produce this low-grade heat to generate some geothermal power. We'll look now at the different types of geothermal power stations that are currently available. This natural gas letdown generator, this uses gas pressure, and what it does is it uses the geopressure of the well, and it can produce 1 megawatt of electrical output operating at 177 to 288 degrees centigrade with an operating pressure of 6,600 pounds per square inch or 42 bar. So here's a simplified flow diagram of the Langston total flow generator and the integrated process flow diagram with Langston Energy total flow generator in the topping cycle. The main component of the total flow generator is a helical screw expander, and what this does is as the either only a gas or only a liquid or even a dual state combined liquid gas fluid passes through the total flow generator, the gases expand and also reduce their pressure. So this can also happen in a gas main distribution system where you have different gas mains operating at different pressures. Instead of just wasting the energy as you go from one pressure to another, you can use the total flow generator to generate power as you're changing pressure. So the Langston total flow generator has an efficiency of 65%. So if you look on the bottom scale here, you can see the various temperature ranges and the different kilowatt outputs from the different temperatures. With the steam turbine topping the Langston things, you also get this extra output results. One of the more interesting generator systems is a 12 megawatt renewable power generator by TurboJam. This is interesting that, for instance, if we wanted to produce a nuclear-sized power station using geothermal as the energy source, then all you'd need to do is connect four of these 12 megawatt renewable power generators in series with each other to produce the 48 megawatts of power, which is equivalent to the Magnox reactor. The lowest temperature design system, as I mentioned earlier, is a deluge. This has an operating temperature of 82 degrees centigrade and uses liquefied CO2 as the working fluid. So again, there's a huge temperature band from high pressure steam, organic Rankine cycle, and the deluge cycle, so that you get many different other generator designs. Is a single borehole geothermal energy extraction system. This works in a hydrothermal field. Basically, it's a single borehole system, which means that what you need is circulating fluids around this downhole heat exchanger, which you would have in a hydrothermal field. And then all you're doing is bringing a clean working fluid up the pipe and going through the turbine, through the condenser, and you have a closed loop cycle in operation, generating power 24 hours, 7 days a week. Another interesting cycle is the cleaner cycle. This claims to have a 50% efficiency improvement. It uses ammonia and water as a working fluid. So again, it can work at medium temperatures, the 150 degrees centigrade to 210 degrees centigrade, but it can also gain up to a 20% improvement in efficiency at higher temperatures as well. So what do we do with the electricity produced offshore? Remember that geothermal is true baseload electrical generation operating 24 hours, 7 days a week, just the same as the Magnox nuclear power stations did. The electricity can be used locally to power the offshore rigs. This means they don't have to burn their own oil or gas, which means there's more available to be sold into the marketplace. Transmitted onshore via electrical cables, which was the reason for the interconnector grids that we talked about earlier. The electricity can also be sold to different countries and therefore create an income back to the UK. It can be converted to hydrogen via electrolysis, which means you're creating an alternative fuel. This can be done offshore, or it could be transmitted by cables and have the electrolysis plants at each filling station, which would remove the need to have petrol tankers and oil tankers delivering fuel to the filling stations. Via electrolysis, the hydrogen can be generated at source where it's needed. It can be linked to offshore wind farms to help smooth supply. The problem with wind farms is you get variable wind speeds and variable power output, but by connecting geothermal into that same power source, it gives you more stability within the source. So thank you for listening to this presentation on geothermal energy. I hope you've enjoyed the presentation, and I hope you will seriously consider using geothermal on your own North Sea oil and gas rigs as an alternative to decommissioning and as an alternative to extending the life of the platform. Geothermal can generate the power needed for the increased pumping of secondary oil recovery. It can also produce the high temperature needed to steam flood the oil fields, extending the useful life of these fields for a further 10 years. So my name is George Lockett again, and please do feel free to contact me if you need any further information. Thank you.